The universe should not exist. Everything around you is made of matter. Your body, the home you live in, the ground beneath your feet, and the planet itself. But according to our best theories, none of it should exist. The Big Bang should have created equal amounts of matter and antimatter, and that should have caused the newborn universe to annihilate itself instantly. But somehow, it didn't. Somewhere, something tipped the balance, and physicists have been trying to understand it ever since. Looking around the visible universe, we barely see any naturally occurring antimatter out there at all. Unpacking why that's the case will require physicists to figure out antimatter's true nature, learning why it didn't stick around.
When we look at the universe, we see only matter in the universe, and there's just no significant amount of antimatter in it. And we ask ourselves where this antimatter has disappeared, and we try to contribute to resolve this question.
So today, we're traveling inside CERN, the world's largest particle physics laboratory, where scientists are creating antimatter in an attempt to understand why our physical universe survived at all. Because in the earliest moments of cosmic history, matter gained a tiny advantage, roughly one extra particle for every billion pairs of matter and antimatter particles. And that tiny imbalance changed everything. It is the reason why galaxies exist, planets exist, and why we exist at all. Behind these walls sits the world's biggest antimatter factory, where researchers trap antimatter in magnetic cages and measure it with an extraordinary precision to search for the tiny asymmetry that allowed matter to survive. Because somewhere in the strange behavior of antimatter may lay the answer to one of the oldest questions in science. Why is there something instead of nothing? In this video, we'll go behind the scenes at CERN to explore how scientists create antimatter, why the universe should have destroyed itself, and how physicists around the world are searching for the tiny difference between matter and antimatter that may explain why our visible universe exists in the form we see it today. Chapter 1: The universe that should have destroyed itself. You can think of any matter or antimatter particle as tiny ripples on a vast ocean. One's a crest, the other's a trough. And when they meet, they perfectly cancel each other out, neutralizing each other. One important distinction to make is that antimatter still has a positive mass, meaning that the energy intrinsic to the mass of matter and antimatter is released as a blinding flash of light. So if there were perfectly equal amounts of matter and antimatter, then it should have all annihilated, leaving nothing behind but pure radiation. This is the radiation that we can pick up in the cosmic microwave background, the afterglow of the Big Bang. We can measure the photons that are left over from the early universe and calculate just how much matter and antimatter must have existed in that split second. We know that there can't have been perfectly equal amounts because the universe around us is made with the remaining surplus of matter. So there must have been a tiny, tiny asymmetry from the light left over from the Big Bang, and from measuring all the matter in the universe, we know that for every billion antimatter particles, there were roughly 1,000,000,001 matter particles, and that small imbalance meant that matter, everything that we see in the universe today, from stars to galaxies, planets, and us, could survive. But where did that extra particle come from? The answer to that question has proved to be one of the greatest unsolved mysteries in physics, and one of the biggest holes in our understanding of how the universe works. To answer that, let's first discuss what even is antimatter. The strange substance was first revealed to physicist Paul Dirac in the 1920s, who wrote down an equation that described the movement of an electron according to both Einstein's theory of relativity and quantum mechanics. But he noticed his equation allowed for an alternative solution, one in which the electron was not negatively charged as we knew it to be, but instead positive. This flip sign meant that it would attract rather than repel a fellow electron. No such particle existed as far as Dirac knew, but the mathematics suggested that it should exist anyway, and physicists christened it antimatter. Physicists then measured the electron's antimatter counterpart, called a positron in cosmic rays from outer space, and realized that it wasn't just the electron. There should exist an antimatter counterpart for every particle that exists. A proton, one of the main components in an atom's big, bulky nucleus, should have an oppositely charged twin, an antiproton. Some of these antiparticles aren't even particularly rare. In fact, you're probably emitting hundreds of positrons every hour thanks to the radioactive potassium-40 in your body. But like with all antiparticles, they exist only very briefly because they quickly annihilate when they meet their matter counterpart, which is what the entire universe, all the stuff around us, is actually made of. But that's only because there's so much more matter than antimatter, which brings us back to the problem this all kicked off with, the matter-antimatter asymmetry problem. Now, quantum mechanics and the Standard Model, our best theory for how matter and energy actually work, has some tiny differences between matter and antimatter. For example, one of the 4 fundamental forces of nature, the weak force, which governs some form of radioactive decay, doesn't treat matter and antimatter completely the same. It has a slight matter-antimatter bias, but this bias is nowhere near large enough to explain why the early universe had an asymmetry. And Einstein's theory of general relativity doesn't help either. But something must have tipped the balance. We don't know for certain, but scientists think the answer might lie in the tiniest differences in how matter and antimatter behaves. An asymmetry, however small, might have created our entire universe and what exists today. But how do you test something that happened 13.8 billion years ago? Well, you go to the one place on Earth where they can create, store, and transport antimatter on demand, the world's most expensive material. At this point in the story, I'm going to hand over to my friend Alex Wilkins, New Scientist physics news correspondent who went to the biggest science experiment on Earth, CERN, to get an inside look at the antimatter research.
Chapter 2, the biggest science experiment on Earth. It's one thing understanding the theoretical physics underpinning the antimatter question, but what if we could create, trap, and study antimatter itself? Maybe then we could start to understand why the universe exists at all. At CERN, scientists are trying to answer these fundamental questions right now, at one of the few places equipped to do it. So I hopped on a short 2-hour flight from London to Geneva in Switzerland, where CERN is based, to see firsthand the place where physicists are literally manufacturing antimatter.
There's only one place in the world that makes antimatter, and it's here behind me at the Antimatter Factory in CERN, Switzerland.
CERN is most famously the home of the Large Hadron Collider, this 27-kilometre underground ring where particles are smashed into each other near the speed of light to try and break physics and better understand the known laws of reality. There's one way that CERN scientists create antimatter, and that's to take those fast-moving particles coming off the Large Hadron Collider, typically protons, and then smash them into a metal target, creating huge amounts of energy. Some of this energy is converted into particles, but a tiny amount of it will turn into antiparticles, which can then be harvested and studied at CERN's Antimatter Factory. Now, there are other ways of making antimatter as well. You can smash the particles into each other, which can then produce even stranger and more exotic antimatter particles. That's the object of study at experiments like the enticingly named Large Hadron Collider Beauty, or LHCb, which I also visited. But the best way to get to grips with all this is to take a tour of the world's largest antimatter factory. This is where physicists live and breathe particle physics. When we visited, every corner we turned around was another antimatter experiment, where scientists were experimenting with mind-boggling precision. Chapter 3, the only place on Earth where we can create and capture antimatter. Christian, good to meet you.
Nice to meet you.
So we're about to go into the Antimatter Factory. This is where we're going to see where all the antiprotons are decelerated and when they can do experiments to find out what antimatter really is made of.
What happens here is the deceleration, and then we have like a network that distributes the antiprotons into different experiments. They were cycled here for 2 minutes in the big ring, 15 seconds in the small ring, and then they are transported out through these beamlines into the experiment area. Then we can catch them there in our trap. We get here around 10 million antiprotons per shot, and we aim to transport something like 1,000 antiprotons. So you have some losses when injecting into the trap. But let's say our trap is not optimized for high efficiency, because in the end we are doing precision measurements actually with single particles in the trap.
When you get inside the Antimatter Factory, you quickly realize just how enormous this operation is. There are 7 different antimatter experiments inside there, all of which are trying to understand different antimatter properties, like what color is antimatter, so what frequency does it vibrate at, how much does it weigh, how is it affected by gravity, and does it work in the same way as regular matter? Would it fall upwards instead of down?
Every atom has its characteristic colors that it likes to absorb and emit. So we're looking for the type of light that antihydrogen likes to absorb and emit. Do hydrogen and antihydrogen have the same exact color? The other thing that we do, which is very fun, is we can take some antimatter and drop it and see what happens in the gravitational field of the Earth. General relativity says that it should fall in the same way that hydrogen does. We proved that in 2023, made the first ever measurement of what happens if you drop real atoms of antimatter.
It's not just producing antimatter here, but also making new antimatter atoms. Down here is the G-bar experiment. This is where they combine an antiproton with a positron to make an antihydrogen atom.
The G-bar experiment, it's one of the hugest setups that we have here. So that there's an electron accelerator here that makes positrons that you need to add to your antiprotons to make the antimatter atoms. And then there's a whole setup of catching antiprotons and then mixing the positrons with the antiprotons to make these anti-atoms.
As you can imagine, all of this machinery is not cheap. It takes vast resources, energy, custom equipment, scientific expertise to produce the smallest amount of antimatter. We're talking nanograms here. That means only enough energy to power a 60-watt light bulb for 4 hours. That puts it among the most expensive materials on Earth, more than 60 trillion with a T dollars per gram. We haven't produced anything even remotely close to that in the entire history of the Antimatter Factory. At current production rates, that would take 1 billion years. But that tiny amount is still enough to learn some pretty astonishing facts about antimatter. The real key to all of this isn't just the creation of antimatter, but the trapping of something so delicate, so precious, that it annihilates on exposure to any regular matter.
We're about to go and see the penning trap, which the antimatter will actually be stored in. A penning trap uses magnetic fields to trap antimatter, to make sure that it doesn't react with normal matter, where it would then annihilate.
From here, so this is the end of the, let's say, antiproton delivery system. So they come here through the floor up, they get bent into the horizontal direction, and then usually they go here into our trap.
So how many antiprotons are inside here right now?
Currently we have around 100 antiprotons inside.
Right.
I can show you the signal.
Yeah, let's have a look. So what are we actually looking at on the screen here? What do these lines mean?
Yeah, so what we have is in principle antiprotons that are sitting in the trap, and they oscillate. They make a harmonic oscillator motion around the trap center, and that has a specific frequency. We call that the dip, where the signal has the lowest amplitude in the middle. That's the antiproton oscillation frequency.
So these antiprotons are basically vibrating at a very specific frequency, and that's what you're measuring as their kind of proof of existence, the proof that they are alive in there somehow.
Exactly. So we call this an image current detection. So the antiprotons move and they induce a tiny current in the ring electrodes that hold them. So we have inside such a stack of rings. Then the antiprotons are moving forth and back. And when they do this image charge is flowing also forth and back. And that's what we detect. And that gives us then this signal here.
So once we've actually got the antimatter isolated inside a penning trap, what can we learn? Once it's there, separated from all regular matter, we can start to probe and prod it to understand its fundamental properties. This experiment was part of the baryon-antibaryon symmetry experiment, or BASE, which aims to unravel the fundamental asymmetry in the universe between matter and antimatter, and rewind to why that happened at the beginning of the universe.
The important thing about the understanding is this symmetry between particles and antiparticles. And this symmetry that we have is very deeply embedded into the theory. So if we discover a breaking of the symmetry, we would not even have a good theory to describe that. So in that sense, it would be groundbreaking for physics to discover a matter-antimatter asymmetry. There might be new interactions or new particles that lead to this symmetry breaking, and that could be an indication for new particles that have not been discovered yet. We want to figure out if the proton and the antiproton have maybe a tiny little difference that we haven't seen yet.
Chapter 4. Are matter and antimatter truly identical? At its heart, BASE aims to work out whether matter and antimatter are truly the same or whether there might be some small difference between them. According to the Standard Model, which is our best working theory of how the universe works, they should be the same. And that is summed up in a principle called the charge parity time symmetry, or CPT symmetry. This is the idea that if you were to reverse any of its properties, like flipping its charge, or its position in space, or its journey through time, then the particle should still look identical in every single way. It would have the same mass, the same lifetime, and the same physical properties. To test this, BASE measures both the charge and the mass of trapped antiprotons, combining it into a single number so it can be compared to regular protons. So far, they've measured it to an uncertainty of 16 parts per trillion. That is the most precise matter-antimatter test ever performed. They plan to test it at even higher levels of precision to see whether CPT symmetry might break at some level, but we don't know what that is yet. In another corner of the factory, we have the Anti-Hydrogen Laser Physics Apparatus, or ALPHA. This builds and studies entire antiatoms, making antihydrogen and then comparing it to regular hydrogen. Now, like BASE, this uses a trapping device, but it also has to create the antihydrogen atoms by combining antiprotons and antielectrons, or positrons. That is much, much harder, adding layers of complexity to the whole operation.
So ALPHA is concerned with the simplest atom of antimatter. We have to produce antihydrogen, which is number 1 on the antiperiodic table. So the idea in theory is that hydrogen, the most abundant element in the universe, and antihydrogen, which we produce here in the lab, should have exactly the same properties. We're putting that to the experimental test with very high precision. The first big milestone was we learned how to hold on to antihydrogen, and we also know how to accumulate it. To give you an example, when we first trapped it, we could get 1 atom every 9 times we tried. Now we get 200 atoms every time we try, and we can accumulate them overnight. So on a typical morning here at the AD, we can have 20,000 atoms trapped.
We've made amazing progress in antimatter studies. Thanks to all of these experiments that we've just seen, we can create antimatter, we can trap antimatter, and we can understand its properties with unbelievable precision. But we're still some way from actually understanding how it works in reality and how it worked at the Big Bang. In this way, the Antimatter Factory is actually a victim of its own success.
When we want to measure with antiprotons very precisely in this facility, we have the problems of fluctuating magnetic fields. We have a lot of radio frequency noise from all the devices.
Despite all the success we've had in creating antimatter and studying antimatter, one thing has become increasingly clear. We need really quiet environments to study this stuff. Somewhere outside the noisy environment of CERN with its radiation and magnetic fields whizzing all around. But is that even possible? We've seen how expensive and tricky this stuff is to study. How do you actually get it out of CERN itself? Well, scientists think they have found a way. Something so audacious it's taken decades to come to fruition. Chapter 5. Antimatter on the Autobahn. BASE STEP is the next phase in the BASE experiment. It stands for Symmetry Tests in Experiments with Portable Antiprotons, and it's all about getting it outside of the noisy environment of CERN, onto the road and into specially built custom labs with minimal magnetic interference.
So we've arrived at BASE STEP. This is the final destination for antiprotons that are decelerated in the hall over there. Once they arrive at base step, they'll be put into the penning trap that we were talking about earlier, which will eventually go onto the truck at the loading bay over here.
What we have inside to sustain it is a liquid helium tank that provides the cooling power while we are moving. And we have a battery system that biases the most essential devices that we need during the transport. One of them is for the trap voltage that gives a voltage to one of these rings so the antiprotons don't move away. And then we have some things that we want to monitor, like the temperature, the liquid helium level, to make sure that the trap is operating at its nominal parameters and that there are no surprises coming up.
And just how fragile is antiprotons? Like, why do they need to be kept at such specific conditions?
They are very sensitive to annihilation with matter. So you need to have an extremely low vacuum. You want to have, in principle, better vacuum conditions than in interstellar space. And interstellar space has nothing, almost nothing in it. So we want even less of that in our antimatter trap. And when the trap starts warming up at some point, you release the gas from the walls that is frozen out, and then the antiprotons annihilate. The other things where we have to be careful is that it is a superconducting magnet. So we have also to keep the magnet below the critical temperature of the superconductor during the transport. And that is for our field at 8.2 Kelvin. So that's the highest we can go with the temperature before we lose the antiprotons.
Do you know how much this entire contraption weighs? It looks quite heavy, but
it weighs around 900 kilograms.
It's almost a ton of cutting-edge science in here.
Exactly. We tried to build it as small as possible, and the dimensions of this thing it's small enough that it fits through a regular door. So you could also bring it to your house if you want.
Maybe in 10 years, we can all have our own antimatter penning traps going to our homes. What is the process of moving antimatter outside of the AD hall?
So the first thing is that we, of course, catch the antimatter in our trap. Then the overhead cranes, they will pick up the trap and lift it. And then they carry it here over the concrete and will lower it on top of the truck. And then we'll tow it on the truck and drive off.
And what kind of truck will it be that is transporting it? Will this be a special antimatter truck?
It's a regular lorry truck that you can open on the top. Nothing too special about it.
A few days after I got back from CERN, I found out that BaseStep had successfully transported 92 antimatter particles across the CERN campus, paving the way for truckloads of tiny antimatter samples being transported across the continent in the name of scientific understanding. Eventually, the plan is going to be to deliver antimatter from CERN to custom labs around Europe with extremely low background magnetic fields. Soon, you could be driving down a road in Europe and next to you will be a truck filled with precious antimatter samples. It will only be then that we can actually study antiprotons free of the noisy environment of the Antimatter Factory and push the precision of how far we can test CPT symmetry to its limit. If we still don't find any differences even at those ridiculously high precision, we can actually start to rule out some of the more exotic theories about how the universe first got its start. That is very useful for physicists because we can start to narrow in on how the Big Bang started.
So now that we have actually transported antimatter on a truck, this means we can start to set up our precision experiments for antiprotons offline and deliver antiprotons from the Antimatter Factory to the offline experiments. And this will enable us to make much more sensitive measurements comparing protons and antiprotons. We'll start using them at CERN, and afterwards we'll spread antiprotons across laboratories in Europe.
And this is the source. This room is where the antiprotons were originated from and will supply labs all over Europe.
Yes.
Visiting the Antimatter Factory, seeing those 1,000 particles vibrating on the screen in Christian's penning trap was an astounding experience. It wasn't just to see the sheer scale of scientific endeavour at work at CERN, but being able to witness the conditions at the beginning of the universe, knowing that if we are ever going to solve the antimatter mystery, CERN will be where it happens. And that's not the only place studying antimatter. Even at CERN there are other experiments. I was lucky enough to visit the LHCb project, a detector on the Large Hadron Collider that looks at beauty quarks. Quarks are a fundamental building block of matter, and they make up larger objects like the atom, like protons and neutrons. The full story of that will have to wait for another film. But there's one even more exciting experiment that isn't at CERN, lying hidden deep inside an Italian mountain. It's probing something even more mysterious and ghostly: neutrinos.
If you're a little bit like me and you're jealous that Alex got to go behind the scenes at the world's greatest physics laboratory, then prepare to have your mind blown. You too can make me jealous and get close to the story with a New Scientist Discovery Tour trip to CERN. On this amazing tour, you'll get an unprecedented access to CERN, learn about particle physics and the cutting-edge research happening right now, including antimatter science. You'll enjoy exclusive guest lectures and guided visits led by practicing particle physicists, and with rare insight into cutting-edge science. And don't worry, no scientific background is required. All you need is curiosity. To be part of this extraordinary experience, curated by New Scientist Discovery Tours, visit newscientist.com/CERN or click the link below. And to get a better understanding of the physics that inspired the tour, let's get back to our story. Chapter 6, The Wider Hunt for the Missing Antimatter. Across the world, physicists are running experiments studying any physical processes that favor matter over antimatter. Remember how I said that one of the fundamental forces of nature, the weak force, has a slight matter-antimatter bias? Well, that gives us an obvious place to look. The weak force is involved in a form of radioactive decay known as beta decay, and the legend experiment, an experiment deep underneath the Gran Sasso mountain in Italy, is searching for a needle-in-a-haystack event called a neutrinoless double beta decay. All of this hinges on the mysterious neutrino, a ghostly particle that is produced in many nuclear processes. In this process, a neutron in an atom is transformed into a proton, emitting an electron. Our current theories say that an antineutrino should also be produced as well. It's not possible for some atoms to undergo just a single beta decay because it would leave them more unstable afterwards. So they need to undergo a double beta decay, and that's where things get really interesting. There's a possibility that neutral particles, unlike protons or electrons, are special when it comes to the differences between antimatter and matter. Neutral particles, like the neutrino, could be their own mirror image. The antineutrino could just be the same thing as the neutrino in every shape and form. If that's the case, a single antineutrino that's emitted from one beta decay can actually connect to the other. And the end result, what we would see, is two neutrons that are turning into two protons, emitting two electrons with no neutrinos produced at all. Now, if a neutrino is its own antiparticle, something called a Majorana neutrino, then that could have influenced matter and antimatter production in the early universe through some pretty thorny physics. But it would be the first identification of a kind of physical process in our universe that could explain why there's so much more matter than antimatter. The first crumb in a longer breadcrumb trail to show why our universe even exists in the first place. Chapter 7, The Experiment Continues. We haven't yet found the chink in antimatter's armor that might explain what went on at the beginning of the universe, but it's still one of the most important fundamental questions. Everything around us exists because of an almost impossibly small imbalance. One extra particle per billion. That tiny advantage that matter had over antimatter determined the fate of the universe. Without that, everything we know and love would not exist. There would just be a universe filled with radiation and nothing else. And we still have no idea what caused it, but we're getting closer than we ever have before. We live in an age where we can produce antimatter on demand, and not just look at it, but store it and measure it as precisely as we do regular matter. This is pushing us closer to the very edge of knowledge, to the point where our physical theories of the universe might break down if antimatter works differently to how we thought. Each new particle collision at CERN every underground detector looking for red decays, and every new astonishingly precise measurement of antimatter is all another attempt to answer one of the deepest questions in science. Why does anything exist at all? But antimatter is only one of the reality-breaking mysteries that CERN is trying to solve. Why don't you click the link on our next video, where we go deeper inside the world's largest physics lab with CERN's head honcho to explore dark matter, the Higgs boson, and why physicists believe we may be on the verge of finding a crack in our understanding of the universe itself. But before you go off, remember to click the like button and subscribe for more videos like this.